The XF-90 was built like no fighter before or since. At a time when no one knew what supersonic flight would do to metal, Skunk Works chose brute force over guesswork. They forged the strongest airframe on Earth, 75S aluminum over a steel spine. The fuselage braced until it was closer to armor than aircraft. It was forged to be at least 50% stronger than any warplane in the entire world. It was meant to ride with the giant B-36 Peacemaker, to dive beyond the speed of sound and deliver nuclear fire across the globe. Then, in 1952, a blinding flash lit up its aluminum skin. The tail quivered, and the landing gear trembled like Jell-O as a shockwave equal to thousands of tons of TNT smashed into its airframe, followed by a mushroom cloud rising into the sky. It was time to see if the strongest plane in the world could take a nuclear blast. While Europe was already exploring the cutting edge of jet technology, the US had focused on meeting the immediate demands of a global war. Early foreign jet programs had been known to US intelligence for years, but they remained small in scale and slow to reach operational service. Germany's Me-262 and Britain's Gloucester Meteor had demonstrated the jet fighters could outperform traditional piston aircraft, combining speed, firepower, and high-altitude capability in ways the Allies had never seen. Until these projects proved their worth in 1944, jets seemed more like curiosities than immediate threats. Industrial and wartime priorities dictated that the focus should be on America's factories producing vast numbers of proven aircraft that were already decisive in combat. Transitioning to jets demanded more than new aircraft. It required new fuel, new maintenance practices, and entirely different pilot techniques. Lockheed, however, had been quietly experimenting with jet concepts since 1939, most notably the futuristic L-133, a radical design with canard forewings and a blended fuselage. Although too cutting-edge to be built at the time, the L-133 showcased the company's ambition and hinted at what could be possible in the near future. When the Air Force finally stood on its own, it faced the challenge of catching up or risk being outpaced in the skies of the Cold War. Strategic Air Command, in particular, placed its faith in ever larger bombers designed to operate at extreme ranges without escorts. This focus on long-range, unaided strike capability clarified the mission requirements for America's next-generation aircraft. They needed to produce a fighter that could keep pace with the enormous Convair B-36 Peacemaker, the centerpiece of the nation's emerging strategic bomber fleet. With a wingspan of 230 feet, a maximum takeoff weight exceeding 410,000 pounds, and an unrefueled combat radius of roughly 3,900 miles, it could carry nuclear payloads across continents. Any escort designed to accompany it would need unprecedented range, high speed, and endurance to operate over thousands of miles of hostile airspace. To meet that challenge, select manufacturers unveiled their most daring creations. North American's F-86 Sabre was the most immediately practical of the contenders. Its 35-degree swept wings, inspired by wartime German research, gave it a decisive edge in speed and maneuverability. Driven by the General Electric J-47 turbojet, producing 5,200 pounds of thrust, the Sabre could reach nearly 690 miles per hour, climb at 9,000 feet per minute, and operate effectively at altitudes above 45,000 feet. Its combat pedigree would be proven over Korea, where it tangled with MiG-15s in the first actual jet-versus-jet battles. For its part, Republic's XF-91 Thunderceptor pursued a more radical approach. Its reverse taper wings widened toward the tips, a bold solution to stall problems at transonic speeds. Beneath its fuselage lay a hybrid propulsion system, a turbojet with afterburner delivering 7,000 pounds of thrust, augmented by a rocket booster capable of short bursts of extraordinary acceleration. In testing, the XF-91 broke Mach 1 in level flight, hinting at the coming era of supersonic combat. Lockheed's XP-90, by contrast, looked every inch the long-range penetration fighter. Its stretched fuselage, swept wings, and robust frame suggested stability and persistence over the thousands of miles the escort mission required. In June 1946, Lockheed received a contract for 2 prototype XP-90s, which were renamed to XF-90 in 1948. The XF-90 was developed under the guidance of Willis Hawkins and the elite engineers of Skunk Works. Guided by Kelly Johnson, Skunk Works had already reshaped aerial combat with the P-38 Lightning and would go on to push the limits of flight with the U-2 and SR-71. Their strength lay in operating as a compact elite team, insulated from the conventional bureaucracy of large defense contractors. This autonomy allowed them to push design boundaries, experiment boldly, and deliver advanced aircraft on aggressive timelines. The XF-90 reflected this philosophy. Every line of its airframe demonstrated a pursuit of aerodynamic refinement and structural strength surpassing that of its peers. A sleek, elongated fighter that stretched 56 feet 2 inches from nose to tail, with a 40-foot wingspan and a height of 15 feet 9 inches. Drawing on experience from the P-80 Shooting Star, it retained the intake and low-wing layout, but introduced 35-degree swept wings, a sharply pointed nose, and fully adjustable vertical and horizontal stabilizers, all intended to provide pilots with precise control during long missions. Twin Westinghouse J-34 WE-15 axial flow turbojet engines produced a combined thrust of 6,200 pound force. Inside sat a pressurized cockpit with an ejection seat and bubble canopy, while designers planned to arm the fighter with 6 20mm cannons. Internal fuel was supplemented by wingtip-mounted tanks, increasing the total capacity to 1,665 gallons, intended to provide the XF-90 with the endurance necessary to accompany the massive Convair B-36. It was the first U.S.-built swept-wing jet to feature afterburners, wingtip tanks as standard, and fully adjustable stabilizers. Beyond its technical feats, the XF-90 was also meant to be an answer to a rapidly changing world, where jet technology was already reshaping the skies. Skunk Works' vision of sleek design and advanced capabilities seemed to be going according to plan, but the aircraft's engine configuration was struggling to move its heavy frame. Pilots soon realized that all the aircraft's aerodynamic refinements couldn't make up for the fundamental mismatch between its heavy weights and limited engine power. Constructed with 75 ST aluminum, heavy forgings, and precision machined parts, its airframe tipped the scales at 27,200 pounds, making it roughly 80% heavier than the F-86 Sabre. At higher altitudes, the engine struggled to maintain sufficient airflow, which limited sustained speed and reduced the energy available for maneuvering, leaving the fighter slow to respond and slow to recover. For all its compromises, the jet's design screamed of a future of American jet supremacy, and it was determined to show it. The XF-90 thundered down the runway on June 3, 1949. Veteran test pilot Tony Levere, already famed for pushing experimental aircraft to their limits, settled into the cockpit. The airframe shivered under the thrust, heavier than any plane he had flown, yet impossibly sleek, like a steel arrow carved for speed. Climbing into the sky, the XF-90 responded, but not with the immediacy the pilot had hoped for. Acceleration was sluggish. Even after full throttle, the aircraft seemed to lumber upward rather than surge. Quick altitude gains required careful planning. Levere had to anticipate the plane's inertia, easing into climbs with gradual, deliberate inputs instead of abrupt ones. Every bank and roll pulled energy away almost as fast as it was applied. Tight turns demanded precise timing, with the slightest overcorrection bleeding speed and leaving the aircraft feeling heavy. The promise of speed and dominance was there, glinting in polished steel, but it remained just out of reach. Still, this test was only the beginning. Engineers and pilots would push harder, determined to perfect the next generation of jet fighters. Then came the dive tests. On May 17, 1950, at Edwards Air Force Base, Levere throttled forward, tipping the nose downward at a surprisingly low altitude. Minor adjustments made since the first flights, including tweaking the ailerons, refining the elevators, and upgrading the instrumentation, helped Levere coax the XF-90 into the dive with slightly more control. Ground observers squinted into the haze as the angular fighter hurtled downward. Then came the boom, a crack so immense and sudden that many on the ground instinctively ducked, fearing the XF-90 had disintegrated in midair. The ground shivered as the shockwave rolled across the test range. For a terrifying heartbeat, LeVier feared the XF-90 might tear apart beneath him. Gradually, the shuddering eased, the wings held firm, and the fuselage remained unbroken. Relief washed over the ground crew and the pilot alike. The XF-90 had endured, its control surfaces were still responsive, and Tony LeVier was unharmed. Better yet, at the bottom of the dive, instruments confirmed what seemed impossible: Mach 1.12. After this, the XF-90 would go on to exceed the sound barrier multiple times, confirming the robustness of its design and leaving no doubt that despite its weight and underpowered engines, the aircraft handled flawlessly. Months later, in the first half of 1952, the second prototype was shipped to the Nevada Proving Ground. Strategists and engineers wanted to know if a jet could survive being near the blast of a nuclear explosion, or at least remain intact long enough to provide valuable data. The first blast detonated in the distance, a blinding column of light that painted the desert sky in molten white. The XF-90 shuddered. The thick 75 ST aluminum of its skin flexed under the invisible grip of the blast. Observers held their breath as the tail and landing gear quivered, but the fuselage remained upright against the growing mushroom cloud. 2 more blasts followed. Each pulse struck the airframe with even more excruciating force. Yet even in this catastrophic display, the XF-90 structure resisted total disintegration, reflecting the solid engineering standards of Skunk Works. The plane was irreparably damaged, but valuable data was gathered on the limits of materials and design in the atomic age. All the tests revealed the hard limits of its design, limitations rooted in the fact that from the very beginning, the airframe had been built around engines and performance levels that simply didn't exist in 1949. Skunk Works engineers assumed that by the time their sleek, long-range escort was ready, jet propulsion would deliver the thrust needed to carry it. However, jet engines lagged years behind advancements in aerodynamics. The XF-90 prototypes flew with General Electric J-34s, the best available in quantity, but they were engine-sized for lighter fighters, not for a brute of steel and heavy aluminum. Afterburning turbojets were still experimental and burned through fuel at rates that made long-range escort missions impossible. Supersonic flight was achievable only in steep dives, far short of the sustained speeds needed for an effective long-range escort. The only American engine with enough thrust, the J-47, was already earmarked for proven aircraft, like the B-47 Stratojet in Strategic Air Command and the Navy's new jets headed for carrier decks. Lockheed's prototype was left at the end of the line. In 1950, as Sabres dueled MiGs over the Yalu River, Lockheed's futuristic escort fighter sat underpowered in California. The Air Force repeatedly highlighted the urgent need for long-range performance, yet no one seemed willing to gamble scarce engines on an unproven heavyweight. Even if they had, the XF-90's mass meant that despite better engines, it would have struggled to deliver the thrust required. While the XF-90 was an ambitious attempt at a long-range escort fighter, the North American F-86 Sabre emerged as an efficient and immediately deployable fighter, quickly gaining favor with the U.S. Air Force. Introduced in 1949, the F-86 was a transonic jet whose 35-degree swept wings reduced drag at high speeds and improved stability in dives and turns, making it one of the most effective jet fighters of its era. Powered by the GE J-47 turbojet, the Sabre could reach speeds around 685 miles per hour and altitudes up to 49,000 feet. It climbed at more than 9,000 feet per minute, outperforming the XF-90's 27,200-pound frame and twin 6,000-pound thrust engines. With drop tanks, it could extend its combat radius to over 1,000 miles, sufficient for many tactical and air superiority missions. The aircraft proved its mettle in the Korean War, engaging MiG-15s in the first large-scale jet versus jet battles in history. Its agility, precise controls, and stable gun platform allowed pilots to counter high-altitude attacks, outmaneuvering the enemy and firing bursts of 50-caliber rounds with lethal accuracy. Dozens of jets spiraled through the sky in chaotic three-dimensional combat, and the Sabre's combination of speed, handling, and operational reliability consistently gave American pilots the upper hand. While the XF-90 struggled under its own weight, the F-86 demonstrated the speed, agility, and reliability the escort had promised. Yet for the sprawling distance of a B-36 mission, what it was supposedly built for, its roughly 1,000-mile range, even with drop tanks, fell far short of what was needed. Lighter, more efficient designs, along with experimental jets, consistently outperformed the XF-90 in virtually every measurable category. Aircraft such as the Douglas XF-91 Thunderceptor, with its rocket-assisted takeoff and mixed propulsion system, showcased bursts of acceleration and climb rates that the XF-90 could never match. With short bursts of extraordinary acceleration, the XF-91 briefly exceeded 700 miles per hour and climbed at remarkable rates, offering a glimpse at how supersonic performance might make long-range bomber escort missions feasible. It was the aircraft's extreme fuel consumption and mechanical complexity that rendered it unsuitable for the endurance and reliability of a bomber escort. Meanwhile, conventional jet fighters demonstrated how practical engineering could deliver agility, climb, and reliability while maintaining manageable weight and maintenance demands. By the early 1950s, it was clear that no contemporary aircraft could reconcile the XF-90's structural heft with the speed and range expected for a bomber escort. Ultimately, the Air Force concluded that none of the designs could meet the demanding escort requirements for the B-36 Peacemaker, leaving the mission unfulfilled. This realization reshaped strategic planning. Rather than relying on long-range escort fighters, the Air Force focused on empowering the bomber fleet itself. Long-range capabilities, higher payload capacity, and eventually in-flight refueling became the pillars of strategy, enabling the B-36 and later bombers, such as the B-47 Stratojet and B-52 Stratofortress, to strike targets across continents without escort. Beyond its technical feats, the XF-90 did something few of its rivals could. It captured the public's imagination, standing for speed, strength, and the potential of America's aerospace innovation. Its streamlined shape made the aircraft a showpiece in publicity campaigns, showcasing the potential of jet technology for both military operations and civilian aviation. The aircraft's design also influenced automotive aesthetics, with car manufacturers adopting styling cues from the XF-90, such as swept-back tail fins and twin exhaust pipes. Posters, magazine spreads, and promotional films showcased the XF-90 slicing through clouds, creating an impactful vision of the nation's jet-powered future. Beyond advertisements, the XF-90 also permeated popular culture. It appeared on the September 1953 cover of Black Hawk, the comic book series, chronicling the adventures of the eponymous pilot and his squadron of daring aviators. Black Hawk and his 6 F-90Bs became avatars of technological optimism in the face of nuclear Armageddon. In 1951, after years of testing and evaluation, the U.S. Air Force officially canceled the XF-90 program. The decision reflected a combination of technical, logistical, and strategic factors. Fuel consumption was high, performance at operational altitudes was limited, and maintenance demands were unusually complex for a production fighter. Additionally, other jet designs offered greater reliability, combat readiness, and practical performance within existing engine and logistical constraints. However, flight data from the prototypes provided invaluable insight into supersonic aerodynamics, fuel efficiency, and high-speed control surfaces. Ultimately, the first prototype's journey ended when it was transferred to NACA, the National Advisory Committee for Aeronautics, for a series of rigorous static tests. Engineers sought to push the airframe to its structural limits, measuring stress points, flex under simulated loads, and overall durability under controlled conditions. In the course of this evaluation, the aircraft succumbed to the very stresses it was meant to endure. Sections of the fuselage buckled, panels tore away, and the XF-90 was ultimately destroyed. The airframe that survived the nuclear tests spent decades exposed to the elements before it was finally decontaminated and recovered. In 2003, it found a permanent home at the National Museum of the United States Air Force in Dayton, Ohio, where it remains on display as a testament to Lockheed's ambitious, if ultimately unfulfilled, vision of long-range jet escort fighters. For Skunk Works, the project was far from a failure. It demonstrated the team's ability to rapidly design, construct, and evaluate cutting-edge aircraft, all while operating under strict secrecy and extreme time pressure. They also experimented with the integration of advanced features that would become standard in later fighters, including afterburners for extra thrust, wingtip fuel tanks for extended range, and innovative armament layouts for optimal combat performance. The XF-90's flight tests provided valuable empirical data on supersonic aerodynamics, fuel consumption at high speeds, and the behavior of heavy airframes under extreme stresses. Lessons about control surface efficiency, structural flex, stability in dives informed not only Lockheed's following projects, but the broader fighter design philosophy. Engineers refined their understanding of how to balance thrust, weight, and durability, paving the way for aircraft that were lighter, faster, and more maneuverable. Skunk Works began to stress performance without unnecessary weight, carrying forward the vision of the XF-90 and laying the foundation for the next generation of high-speed jet fighters. It all culminated with the F-104 Starfighter, whose slim fuselage, blistering speed, and operational characteristics bore the clear imprint of the XF-90's experimental groundwork.